Hi everybody, video is going to show you how to utilize MATLAB to do some elementary polynomial curve fitting. Um, if you looked at the agenda that we had for the curve fitting part, we had a couple exercises in which we were going to ask to do for a couple sets of data is to plot the data to see what type of degree of the polynomial might be necessary to be able to fit it best. We're going to use MATLAB to find the coefficients using the polyfit function. And then what we're going to do is we're going to create a function to model that data. And then finally, we're going to plot the data and the model on the same graph to get an idea of the residuals and to see maybe perhaps how close the model is to the curve itself. So the first thing we're going to do is we're going to start by using the basic CLC and then the clear all commands. So that way we can prep ourselves to be able to execute this. Another thing that I'm going to do is I'm going to define two variables, x and y. I'm going to enter the data into two matrices. So I'm going to say something to the effect of the x data and the y data. So we're going to say, let's just call it x dat is going to be equal to the first set of x's, which is going to be 2, 3, 5, 6, 8, 9. And then for the y data, and I'm going to suppress this with the semicolon. For the y data, I'm going to call that y dat, and that's going to be equal to the y coordinates. So we just go up here, and we see the y coordinates are going to be 3, 4, 5, 7, 8, 10. All right. Now we're going to plot it. So we're going to say plot x dat, comma y dat. And we're going to use a specific marker to make the scatter plot. Otherwise, it's going to try to connect it with a line, and you'll get some sort of line graph as opposed to a polynomial function. So you can use this, the lowercase letter o. You can also use an asterisk if you want to. That's a pretty cool one. There's a lot of different options you can use. All right, I'm just going to use the o there. I'm going to run this, and then I'm going to have to switch the screen once this executes to show you what it's going to look like. So I'm going to stop share really quick, and then I'm going to share what the polynomial looks like. And hopefully you can see this, but if not, it does illustrate that it looks like it's going to be a linear association. All right, so maybe I can try this one more time. I'm not sure, but just to verify, let's do a new share. And we're going to share the figure. So it looks like it is sharing that. So pretty clearly, a linear association would probably be the best fit for these 6 data points. So now how do we get that? Okay, so I'm going to close this, and we're going to go back to the MATLAB. All right. And so what we're going to do is we're going to use a function called polyfit. Okay, so I'm going to say P is equal to polyfit. And there's 3 commands, or there's 3 parameters that we have to put in there. So we're going to say x dat for the x data, the y data, y dat, and then this last parameter is going to be the degree of the polynomial, which in this case is going to be a first order polynomial. Right? Now I'm just going to run this, and I'm going to comment the plot out. I'm going to run this just to illustrate what happens when we do this and what the output looks like. Right? So I run it. And this is what we get. And we get 2 numbers out of this. And what those numbers are, those are the coefficients of the polynomial in descending order of degree. So in other words, our polynomial we can write as 0.9467x plus 0.9600 to model the line. All right, so what we're going to do is I'm going to say that y is going to be equal to the first element, okay, because now this is an array, this P or a vector. So we're going to say P1 times X. So the first element in the array coordinates with the first power, and then plus P2. Now I'm going to suppress the polyfit, and I'm going to execute the program to show you what the output looks like now. And now y is equal to this function. So 71 75ths x plus 24 25ths. It's a linear association. And then let's go ahead and plot that on the same graph as the scatter plot. Okay, so here's our plot. Now I'm going to do a hold on, and I guess before that we need to define a domain for x. So let's say x is going to be equal to linspace. Notice that we go from 2 to 9 in the domain. So I'm going to create a vector of numbers from 1 to 10. And linspace, what that does is just says x is going to be numbers between 1 and 10 in increasing order, similar to a vector array. So basically, I'm just making it so that it can plot the points. All right. Now we know that y is going to be equal to 71 75ths x plus 24 25ths. And now what we can do is we can plot both functions on the same graph. So we're going to plot the x dat and y dat. We're going to do a hold on. We're going to plot x and y. And we don't want to scatter plot. We just want to line this time. So we're not adding in that third parameter. And then we're going to turn the hold off. All right, now let's see what this does. And again, I'm going to have to share the screen or flip the screen. All right, and let me flip the screen, hopefully. So I'm going to do a new share. And here's our new figure. Clearly, the function that we got is a linear function that indeed is a pretty good model for the scatter plots that we just put together. All right. Clearly, this is a good way to illustrate to students the importance of being able to use the polyfit function to model data. And this could be especially useful in their lab classes like biology, to relate some sort of exponential relationships, or even in quadratic relationships, even in chemistry to show some sort of reaction time versus amount of some sort of chemical that's left. All right, so definitely something that could be useful to students. All right, so I'm going to show you another example. So let's go back. All right, and set 2, all we're going to do is we're just going to change the data points. Okay, so instead of having x go 2, 3, 5, 6, 8, 9, we're going to have -3, -1, 0, 4, I'm sorry, 0, 2, and 4. And then for the y data, we're going to have -22, 0, 4, -9, and -42. Right? That's the data that's given to us. Now I'm going to comment everything out for now, except for the plot, because we want to see what type of scatter plot we're going to get this time. So I'm going to run it, and I'm going to share the screen with you. It does come up. Okay. And I'm going to share, new share, figure 1. All right. And so here's our graph. And what you'll notice is that this time we get more of a quadratic relationship. So we could probably model this very nicely using a second order polynomial. Right? So that's what we're going to do. So let me stop sharing this. And we're going to do the exact same stuff as before. We're going to have to change a few parameters, and it's not going to be too difficult. So let me go back to the MATLAB. Now, we're going to say P equals polyfit. But this time, instead of a first degree polynomial, we're going to have a second degree polynomial. Notice x ranges from -3 to 4. So I'm going to change the linspace. I'm just going to go from -4 to 5, just so that way I have one more additional variable. I'm going to change the function of y to P1 is, or P1 times x squared. And because we're doing this on an array, we have to use the dot to indicate that we're going to be using a vector, right? And then P2 times x plus P3. Right? So there's going to be three terms output because we have a second order polynomial that we're modeling. Everything else now is going to stay the same. So I'm just going to execute this, and I'm going to take off what y, or what the polyfit is, so you can see what the coefficients look like. So let me go ahead and execute this. Right. And here's our polynomial coefficients. Remember that the parabola, or at least the scatter plot, had a concave down association at the vertex. All right. So the first coefficient makes sense that it is negative. All right. The rest of them doesn't necessarily matter too much. But the best thing we can do to see how good of a relationship we can get, or that exists, is we can take a look at the scatter plot, and without computing the residuals. So let me just share that scatter plot. All right. And clearly, it's almost like somebody picked out the points to be able to make them fit very nicely, which somebody did. So this is a good illustration, hopefully, of how to be able to put together these polynomial fitting exercises that could be very useful to your students as they go along and try to create mathematical models for data to simulate these sorts of natural or different types of natural phenomena. So the next series, what we're going to be taking a look at is we're probably going to be taking a look at being able to do file sharing, and we're going to be able to write and read from text files and CSV files.